Let me just label this up here so I can save a little more space. That's value for A. So B, how much work does Lola do in pulling the mouse to this position? So what we have to look at here is basically what's the change in Lola's kinetic energy and what work is done on her by different things. So change in Lola's kinetic energy from state 1, I'm going to call it here, to state 2, so that's what we're looking at, is going to be the sum of all work done on Lola, okay, which is going to be the work done by, what are the forces on Lola? Well, the work done by gravity plus the work done by static friction plus the work done by the normal force plus the work done by the spring. And so gravity and the normal force do no work on her because she travels horizontally and those act vertically, right? Here's gravity going down, here's normal force going up. When she travels horizontally, they do no work. And then you have the work done by the spring, which is a changing force, and the static friction force, which is changing force. However, we also know that Lola starts and ends at rest, or that's what we're assuming, okay? So really what we have is the work done by static friction, which is the work Lola has to do effectively by moving her legs while the static friction is acting on her. That's like, imagine you're standing still and then you start running, okay? What's the force that does work on you? What's the external force that allows you to run or allows you to accelerate? It's static friction, but you're doing the work in your muscles, so it's a similar thing for Lola, okay? So this WFS is the work Lola has to do, so this is going to be the answer. So that comes down, and then the work done by the spring, since spring forces are conservative, that's the change in spring potential energy. So in fact, the work Lola does, and I'm just going to, well, I'll say work by static friction, but it's the work done by Lola, okay? Is equal to the change in spring potential energy, okay, which means it's the spring potential energy at the at state 2 at the end when she's done pulling it, minus the spring potential energy in state 1, okay, which is now her final spring potential energy is going to be 1/2 k x squared, and her initial spring potential energy will be 0 because the spring is at its relaxed position at the beginning. So basically the x here is this extension here. K is, of course, this given spring constant. And so all you have to do is use 1/2 kx squared, and you find the work Lola does, which is, so 1/2 0.5 times k times 1.8 squared equals 13.77, 13.8 joules, okay? So B, the answer is 13.8 joules. Okay, so that's the work Lola does. And then part C, when Lola releases the mouse, what is its speed at the instant when the cord reaches its relaxed length? So what happens is the mouse goes from here to here, okay? And here it has an initial velocity of 0, okay? So V equals 0 here. Or here you can call that state 2, and then at state 3, when the spring reaches its relaxed length, it's got some speed it's going there, okay? Or some speed the mouse is going there. So let me clear off some space on our little whiteboardy thing. Okay, and so let me just switch colors again to black. Okay, so at state 2, well, so what's the work done on the spring? Or you can look at the spring then and the mouse as an energy conserved system, okay? So, or a system where mechanical energy is conserved. So at state 2, mechanical energy, this is actually true everywhere, okay? At state 2, mechanical energy is going to be kinetic energy of the mouse plus potential energy of the spring plus potential energy of gravity, okay? So I'm not going to do that yet. And what we can do then is say, let me switch to, I need a better palette of colors. Oh, wow, that's a helpful one, right? Okay, so let's go like some kind of dark green. That'll work. Okay, so what we can say, first of all, we're told to neglect the mouse's weight. And so that means we can say that UG equals 0 because we're neglecting the mouse's weight, okay? Remember, the potential energy of gravity is the work done by the weight of the object as it goes up and down, okay? So we were given permission to neglect the weight, and that makes this problem much easier, because otherwise it's basically it's impossible to tell exactly where the mouse is going to be when it reaches the relaxed length, what height it's at, and that would affect the potential energy. So, you know, you can't even worry about that. So now we just have to worry about the spring and kinetic energy of the mouse. So at state 2, which I'm going to say is when the mouse is launched, or when Lola lets go, and 3 is when the spring reaches its relaxed length. State 2, kinetic energy is 0, and spring potential is 1/2 kx squared, which is just this, okay? It's the energy that Lola put into the spring by doing work. Literally all the work Lola does goes into the spring in this, okay? And then state 3, k equals, 1/2 mv3 squared, and that is what we want to find here for part C, okay? And us equals 0. And so now we do EMAC, which is k plus us at state 2, is equal to EMAC at state 3. EMAC 2 equals EMAC 3. And we just say 1/2 kx squared equals 1/2 mv3 squared. Oh, sorry, not cubed, squared. Okay, so obviously 1/2s go away. Or, you know, actually you could not do that. You could just say, well, we know this is 13.8 joules on the left, right? So I'm just going to leave it as 13.8 joules equals 1/2 times the mass of the mouse, which is 20 grams, so 0.020 kilograms, okay, times V3 squared. And if you do all that, what you get, okay, please pause while Dr. Smith types numbers into another computer. So, and then divide by 0.02 equals that, and then so it's the square root of 1,380, and the square root of that is 1,380. Okay, so the mouse is going about 37 meters per second, which oh god, crap, I hate that. Okay. Oh, I don't know what to do now. Okay. This is so obnoxious. Okay. Okay, well, whatever. I don't want that. Okay. I don't even know what's going on here anymore. Okay, well, we're in a state of disarray, but V3, when you solve this, okay, sorry, V3 squared, okay, V3 is going to equal 37.1 meters per second, which is not, I really doubt that's how fast it goes. Probably I have the spring constant a little too high. I don't know. I jiggered with the numbers to make them work nicely. Anyway, there you go. That's the answer to the problem, more or less. Good luck on the test.